Hello students, in this video we're going to continue our discussion of Chapter 10, Analysis of Variance. In the previous chapter we were working on this example with the 22 young calves being assigned to 4 different feed systems. We determined, based on the test statistic and critical value and again on the p-value, that we are going to reject the null hypotheses, basically stating that we have enough evidence to indicate that the average weight in the 4 feed systems are not equal, that perhaps one of them is better than the others. So once we have that decision, we can actually carry out various tests to determine which of the treatments, or in this case feed systems, are better than the others. This process involves calculating and determining confidence intervals. So once again, this is only done when the ANOVA test is to reject the null hypotheses. Confidence interval is determining the difference of 2 populations using the following formula. So we're going to be looking at this. This is basically looking at the difference between 2 sample means using a t-value, MSE number from our summary output, and then the sample sizes from the 2 populations. So this t-value is found using n minus k degrees of freedom. So in this example we have 22 calves, we have 4 treatments, so there's going to be 18 degrees of freedom. Alpha divided by 2, alpha in our example is 5%, so we're going to be finding this t-value using half of alpha, or 2.5%, 0.025. By looking at the average values in the output summary, we may be able to determine which pair of treatments has the highest chance of being more significant, or which one has a better chance of being different, or greater than the other ones. So we can go back to our data. Let's go here, calf summary. So treatment 4 has the best weight gain, 86.8 kilograms. Treatment 4 has the worst one, so this is more likely going to be the one that's going to result in a significant confidence interval. So we're going to look at compare feed 1 versus feed 4. Sample size of 1 is 4. Sample size of 4, feed 4, is 6. And here is our MSE value, 38.98. This is one of the values we need in our confidence interval formula. We also need a t-value. Our t-value, we know that alpha is 5%. We divide that by 2. And degrees of freedom, n minus k. So here is our correct t-value. So when alpha is 5%, we are in essence developing a 95% confidence interval for the 2 different population means. So 95% confidence interval gives us this column, and 18 degrees of freedom, 2.101. Go to a writing board here. Basically, develop this confidence interval for treatment 1 or feed 1 versus feed 4. The average for feed 1 was 86.8. Average for feed 4, let's go x bar 1 and x bar 4, was 68. 68.8. Sample size for feed 1 was 4, and the sample size, let's get rid of that. Sample size in 4 was 5. So our confidence interval formula is built that we're going to take a look at the differences between the sample means. So 86.8 minus 68.8 plus or minus the t-value. We know the t-value is 2.101. 5% level, or 95% confidence interval, alpha is 5. Divide that by 2 and looking at 18 degrees of freedom. This is multiplied by the square root of MSE, which is from that summary output, 0.98 multiplied by 1 over sample size 1 plus 1 over sample size of 4. So 1 over 5. And that should just be a nice little addition. Not sure what that looks like, but let's just, there we go. So if we do this math, we're going to get a difference of 18 plus or minus, carry out this whole calculation, we will get approximately 8.8. At this point, what we want to do is find the endpoints for the confidence interval. Endpoints are going to be an upper limit where we add these two values. So basically 18 plus 8.8 gives us 26.8. And the lower limit, 18 minus 8.8 gives us a value of 9.2. So because we took a sample, we are basically 95% confident that the difference between feed 1 and feed 4 is somewhere between 9.2 and 26.8 kilograms. Because both of these are positive, both of the endpoints are positive, we can conclude that feed 1 is better than feed 4. Feed 1 is going to outperform feed 4 anywhere from 9.2 kilograms to 26.8 kilograms. Somewhere in there is a true population difference. Because both endpoints are positive, we can make that conclusion. If they were both negative, we can make the same conclusion. We'll see in the next example that if one of the endpoints is positive and one of the endpoints is negative, we can't make this same conclusion. Generally, what we do is we assign the greater average back up here. It's just easier. This one is going to be X1, sample 1 is going to be the larger average. And the second average is going to be the lower average. This basically means that there's going to be more of a chance that both are going to be positive. But now let's take a look at perhaps a different pairing. Let's look at, so we have made a conclusion that feed 1 is better than feed 4. Feed 1 outperforms feed 4. Let's take a look at this difference here. This is probably the smallest difference, feed 3 and feed 4. So is there any evidence, significant evidence to indicate that feed 3 is better than feed 4? So let's carry out this process using these numbers, 72.9, 68.8, 7 count for feed 3, and a sample size of 6 for feed 4. So let's just go here. We're looking at basically feed 3 versus feed 4. The average for 3 was 72.9, and the average for 4, 68.8. So mathematically, the calves in feed 3 did gain more weight than the calves in feed 4, but is that difference significant? Or is it just due to sampling error? So we know that our sample size for 3 was 6 calves. Sampling size for 4 was 7 calves. We put this into our confidence interval formula. We're going to go 72.9 minus 68.8. Plus or minus, it's the same Z or T value, 2.101. It's the same MSE number, 38.98. The only difference here is the sample sizes, 1 over 6, 1 over 7. Making sure I got those numbers right. close. 1 over, let's just make that. This is 7. This is 6. And won't make any difference here, but let's just be consistent. So this is 7. This is 6. 1 over 7, 1 over 6. So now we can carry out this calculation. This results, the difference is 4.1 plus or minus 7.3. When we find the endpoints of the upper limit, it's going to be 11.4. The lower limit is going to be negative 3.2. Because one of the limits is negative and one is positive, they mean they have opposite signs, we cannot conclude that feed 3, oops. Let's just write this here, that feed 3 is better than feed 4. There's no statistical difference between feed 3 and feed 4. Basically left with the conclusion that there is potential that feed 3 and feed 4 could be as great as 11.4, but there's also potential that feed 4 could be better than feed 3 up to that 3.2 range. That's how we could interpret that. So because of these signs here, this is positive and this is negative. Let's just highlight that. Right, because the signs are opposite. We can't make the conclusion that one is better than the other. So statistically, they would be viewed as being no different. So we look back at our data, we have 4 systems. So we could do the same test basically 6 different ways. We could go feed 1, feed 4, which we did. We could go feed 1 versus feed 3, feed 1 versus feed 2, feed 2 versus feed 3, feed 4 versus 2 versus 4, and then the one we just did. So these would be the 6 tests that we could run. We have determined that feed 1 is better than feed 4. So if the question is to determine which of the diets or treatments or these feed systems are better than the others, we know that feed 1 is the best. Feed 1 is better than feed 4. We could go through the process to determine if feed 1 is better than 2 or if 2 is better than 4, but ultimately, this agriculture example, they may be only looking to determine which is the better feed, which we have done. So that is our analysis of variance section. Remember, we do this confidence interval only if the overall decision has been to reject the null hypotheses.